Greetings, good sirs and madams, and any other gender as well. On this little video, we are going to try and talk about mathematics, in particular, algebra. Some people just don't get this, and we hope we can make some sense out of it for those who don't. As the name says, this is the sense group. We want to say this is intended to be a pilot for a potentially longer math series that may go further, and perhaps backward as well, to eventually be a complete program covering many different areas of math, but there's no guarantees. Before we begin, though, we will want to first mention the prerequisites, and that is that you should be familiar with arithmetic, how to add, subtract, multiply, and divide numbers, as well as basic facts and rules of arithmetic, with these like the fact that addition is commutative, that is, things like 2 plus 3 equals 3 plus 2, and to be familiar with arithmetic notation and the meaning of arithmetical expressions. Logic might also be useful as well, and we may make a video on that soon. But we will start with this algebra because it seems to be a sticking point for many in schools. We hope these explanations will be useful. We won't be explaining the uses of algebra here, though, at least not for this first video. Rather, our aim is to focus on algebra itself, in particular, to get a clear understanding of the foundational principles, because without those, it is a struggle to understand the rest, and they may not be taught as clearly as they should be. In particular, we wish to explore the rules of algebra and why they are the way they are, because a big problem of understanding math, we believe, is simply memorizing rules and not really understanding the reasons behind them. But there are very good reasons why the rules are the way they are, and we shall explore those in this video. So with that out of the way, if you want to go ahead, here we go. Algebra, roughly, starts out with something like this. This shows a very simple equation, a mathematical expression which asserts that it is true that two things are equal to each other. In particular, the number 5 equals the number 5. Everyone should agree that this is true. If you don't, I wonder why. Equality means two things have the same value, so clearly 5 should have the same value as itself, no? But now suppose we do something like this. Let's just play around and see what happens. I'll add 6 to the 5 on the left. And if we carry through that addition, we get this. Do you believe this is true? Surely you should not. And indeed, it isn't. The question comes up then, given that we are here, what can we do to make it true again? One answer is rather obvious. Just subtract 6 again, and that would take us back to where we started. But that's not very interesting. Let's go back. So what else can we do? We could try to add something else to 11, but it would still not be equal, unless we added -6. But that's what we already did. So the only other option we have to restore equality is to do something to the other side. What should we do? Well, one answer is fairly obvious. Just add 6 to it, as we did on the left. There we go. But is it the only thing we could have done? Let's go back. Let's suppose we multiply the right-hand side by 2. Then add 1. This works, giving us a true equation at the end. But is it really a good idea? It'll become clear later that it is, in fact, not. But we can't entirely satisfactorily explain why right now. Thus we will agree to instead stick to the rule that whatever operation you do to the number represented by the left-hand side of the equation, you will do the same operation to the number represented by the right. We can, however, right now, explain this part of the rule, that the operation must be done to the represented number. This is an important caveat, for which it will take an equation a little more complicated to understand. Consider instead this. You should verify for yourself this equation is true. Suppose, if we were given something like this, that we tried to add 1 to the factor 2 in there, like this, we might be tempted to do exactly that. We might think to make this go, we should also add a 1 to the 4 in there, since it is, after all, in the same place in the product, like this. Let's just do that. Oops, that didn't work. Why? The answer to this is that this operation we did was dependent on the fact we had written the numbers in a particular way as products. More specifically, it depended on the fact we wrote the left-hand number, which is equal to the number 20, as 2 times 10. When 20 is written in this form, and we add 1 to the left factor, we get 3 times 10, which is 30. But had we written 20 as 1 times 20, adding a 1 to the left factor would produce 2 times 20, or 40. What this means is the operation we've attempted to do in this scenario produces different results depending on exactly how we express the number as a product, and it would make no sense had we written it as a sum. Were the right side, say, 10 plus 10, how could we do this operation of add 1 to the left factor when there is no factor? That is, this operation, when viewed as an arithmetic operation upon a number, here 20, or 2 times 10, or however you want to express it, is what a mathematician would say is not well defined. It is too involved with the vagaries of representation and not with the thing actually represented. Thus we will reject this operation as part of our algebraic toolkit. But if we do something like this is okay. The parentheses allow us to set up the expressions aside as complete numbers to highlight what is actually going on. We can, of course, drop them because the order of operations ensures the result will be the same. Indeed, the order of operations is designed, in part, to make things like this possible. Note that in this case we have also changed the 2 to a 3, but we've done it in what is a mathematically well-defined way, since adding 10 to a number is, as we should all agree, a well-defined operation. There is one and only one possible number you can get from doing so, no matter how you choose to represent that result, whether you want to factor it into a product, or you want to rewrite in Roman numerals, or anything else of the sort. It's very important to keep in mind in mathematics this distinction between the representation of a thing and the thing so represented. The number 30 is one thing, whether it is written as 30, the English word 30, the Roman numeral XXX, or anything else of that sort. The same thing can have many different representations. Of course, we can then start delving into philosophy, like whether or not there exist any objects independent of the representation, in what sense and to what extent mathematical objects exist at all, and issues of that type. But let's not get off on a tangent, although that's very interesting to explore in its own right. We're here to discuss math, not philosophy, although the two, as we can see here, are not really that far away from each other. For now, we will imagine there's this thing called the number 30, and that all these representations are referring to that same thing. Certainly, this thing we've imagined proves to be very useful in our daily living. Continuing with our original example, you can see that as long as we follow this rule of doing the same operation to each side, so long as that operation makes sense operating on the number represented, and not the representational, we get valid equations, which should further serve to convince you of its truth. There you go. You should practice this more in case you don't get it. Now, we are going to go a step further and introduce the first really major concept that distinguishes algebra from arithmetic. We have seen so far equations involving only explicitly specified numbers and operations. What we will do next is something new compared to purely arithmetical drills. That is, we will introduce something called a placeholder, which can be replaced with a number or with another expression, but itself is neither of those things. It can participate in mathematical operations as though it were such a thing. You can think of it as like the wild cards or jokers in card games like poker, which functions the same way in the hand as any other card does, but its denomination can be freely, or not so freely, chosen by the player, ideally to maximize your advantage in the game. Mathematicians would call this a variable, but we'll stick with calling it a placeholder for now. Indeed, just as in card games, there can be restrictions as to what values a variable can take, but we will not get into that in this basic treatment, so as not to bloat it. Perhaps maybe we should use this symbol instead. No, but you should get what we're driving at with that. If you haven't played any of these games, don't worry about it so much. This, again, is an equation. It asserts now, though, that the number in the placeholder is equal to 1. In particular, in logic terms, and we'll get a video on logic too, this defines what is known as a predicate on the placeholder. A predicate is a sentence which can be either true or false, depending on the values one assigns to one or more placeholders or wildcards within it. If we substitute 1 for the placeholder, we get a true equation. But if we substitute something else, the equation becomes false. Substituting an arithmetic expression which has the value 1 will also work. Again, you should see the equation is true, but if we take anything that is not 1, you should see that it is false. We call a value that, when substituted for the placeholder, makes the equation true, a solution of the equation. And in this case, the equation is only the solution 1. In particular, whenever we have an equation of this form, with one side but nothing but the placeholder, and the other nothing but numbers or arithmetic, we know that the only value of the placeholder that makes it true is that of whatever is on the other side. To see why this is important, let's consider a more complicated equation. Do you know what value makes this equation true? But suppose it weren't so easy. How would we find the value that makes it true? Well, if only that plus 3 weren't there, we'd have an equation with a placeholder on one side, and only numbers on the other. So how can we make it go away? Think back to the previous work we did, where we started with 5 equals 5. We said that if we did the same thing to the number represented by each side, the equation would continue to be true. So let's suppose it's true for some value of the placeholder we don't know. What do you have to do to clear the 3? How about this? And you should know from arithmetic that if you have something like this, the subtraction cancels out. And thus we now know what the placeholder should be to make it true. Try it yourself with these. Get some paper and pen or pencil and try this out. Make sure you understand why you're doing what you're doing. This is also where we can explain the rest of why we said earlier that we said we had to do the same operation to both sides, and not just random operations, to make the two equal, even though we showed a case where that could be done. This is why. Suppose we had something like this, in the spirit of our earlier example. In the first equation, it worked that if we took the wildcard to be 5, the equation would hold true. But in the second equation, 5 does not work, instead producing the false equation 11 equals 10. What this tells us is that if we do an operation to only one side of an equation with a wildcard in it, but not the other, the solutions to the new equation may not be the same as to the old equation. Well, in this particular case, we could do a few more of these one-sided steps and get an equation with the same solution 5. We can only really choose these steps well with foreknowledge that 5 is the right solution. If we did not know that ahead of time, and we usually don't, we would be in trouble. In mathematics, we want to stick only to steps that are guaranteed to give us the correct result, not to go out on limbs that work in some cases, but not in others. Sticking to this rule assures that as we transform and modify the equation, solutions to the previous form of the equation are also solutions to any succeeding forms, and so, right on up to the final form, where there's only the placeholder on one side and only numerical calculations on the other. There's a subtlety in this, however, which we'll see when we get to more complex equations that have multiple solutions. The process we have shown that of reducing an equation to one whose solution is completely transparent is what is known as solving the equation. We will now illustrate how to solve the given equation correctly. You should understand these steps. See how that worked? Now, as a note, we would usually not use the star symbol in this case, instead just write it like this. And observe that the convention is the number appear to the left of the placeholder. Now you try it yourself with this. Is that so difficult now? To understand the concepts involved here. One more thing. It's also important to not get too hung up on the symbol used for the placeholder. We used a question mark, but all the same steps apply where we use something else. Here's an example. There's also no restriction that the placeholder appear only on one side. Consider this. While there's a lone placeholder on the right, that doesn't mean we can automatically read off a solution, because it's also on the left. In this case, we really get to exercise the notion of the placeholder as standing for a wild number. Note that wherever it appears, the same placeholder symbol stands for the same number, whatever that number is. One number, one symbol, multiple appearances. This step may require a bit of explanation in light of what we said before, since we said we could not operate on one side only, and one may be confused by it. This step is okay, because rearranging does not change the number represented by the left side of the equation due to commutativity. Now you can solve that part as we did before. This should give you a negative number. And with that, we conclude our simple introduction to the basic ideas of algebra, and also this pilot video.